In this video, I'm going to discuss how to perform linear regression with two input variables. Once again, we will use the PIMA diabetes dataset. And the question that we would like to ask here is, can we predict someone's age knowing their blood pressure and BMI? So as usual, I'm going to download the dataset and then load the data using pandas and observe the first few rows. So to do machine learning, we would definitely load the data set using a NumPy array. But before we do that, let us do some preliminary analysis. Since we are interested in these three variables, blood pressure, BMI, and age, what I'm going to do is create a 3D scatter plot and see if there is obvious relationships that I can see between these three variables. Since I'm interested in the three variables, blood pressure, BMI, and age, I'm going to draw a 3D scatter plot of these variables. For this, I can simply do px dot scatter 3D and then supply my data frame here, which is the data, and then choose my x equals to my variable name, y equals to my variable name, and z equals what I want. So my x will be one of the variables I'm going to choose is obviously blood pressure, BMI, and age. I'm also going to set opacity equals to less than 1 so that I can see the overlapping data points as well. So if I run this, I'll get a 3D scatter plot, which I can rotate, play around, and see the relationships. So from this side, if I look at the relationships between blood pressure and age, there is some correlation, but not much. As blood pressure increases, age also increases. We can also check the relationship if there is any between blood pressure and BMI. So here we see that between blood pressure and BMI, as blood pressure increases, we see that BMI also slightly increases. So in this way, I can observe or play around with the scatter plot to check the relationship between my variables. Now, as we did before, we can load the data set into a NumPy array, and then we're going to do the standard neural network model building process. We do model equals sequential, and then we add a dense layer to the model. Now this time we set input dim equals 2 because we have two input variables. Then we do the standard model.compile and model.fit. Now our X here becomes give me all rows, but as columns, I want to select the first column and the second column too. So the range should be 0 to 2. So this tells me that my X, I can even specify X equals this so that I know that the inputs are two columns. And then my Y will be the is, which is all rows and the third column. And then I can do the training of this model. I see that the loss is around 150. Let me go back and retrain the model. So to retrain the model, since I want to keep everything same, that is keep the weights as it is, and then continue my training, I'm just going to copy the model.fit and run it again for the next 256 epochs. So I see that the loss is even going down up to 146. So I'm going to set verbose equals 0 and increase the number of epochs to around 1024. So I get minimum possible loss. So now obviously the next thing that we would like to do is make predictions from the model and check how the model is doing. And we can do this by doing predictions equals model.predict. And then I can pass all of my data points, input two columns, data set, all rows, 0 to 2. So I have all of my predictions in this variable predictions. And just to make things clear, true ages equals, we would like to keep the true ages into a new list where I do data set, give me all rows and the third column. So here I have my predictions and here I have my true ages. So if I'd like to see how the predictions are, I can simply do print true ages, and let me print the first 5 values. And I can also do, so I can run this, these are my true edges, and I can also do print predictions and the first 5 values. Now I know that this is transposed list, so I can simply transpose it back to get a list that I can see. So here are my true values: 50, 33, prediction is 33, 31, prediction is 31, 33, prediction is 28, and so on. Now to get a quantitative assessment of how the model has done, we can calculate the absolute difference between the errors. So difference, diff equals absolute difference between true is and predictions. Now since these prediction values are actually two-dimensional arrays, which effectively actually it's a list, but it's presented as 2D array, I can simply flatten this, flatten it to make it a plain list. So this gives me the difference between true and predictions, absolute difference between them. So let's see how some of the errors look like. So I can do diff, let me print the first 5 values, and I see that here are the errors. So for the first is, the prediction was off by 16. For the second is, the prediction was very accurate. For the third is, it also very good prediction, and so on. Now, one really nice way to compare true versus predictions, that is, compare true versus predictions, is to simply draw a scatter plot between true and predictions. So for this, I can do import matplotlib.py plot as plt. I get this running so that I can autocomplete other features. And then I do plt.scatter, then I plot predictions versus true. So true is in my x-axis and predictions in my y-axis. Once again, I'm going to flatten it so that this both become list. And I'm also going to add labels. So if I visualize this plot, this is how it looks like. Now in this plot, it is difficult for me to compare true edges with predicted edges. So I'm going to add a diagonal line to this plot. And I know that edges usually range from 20 to 80. So my x is going to be 20 to 80, and my y is also going to be 20 to 80. I'm also going to give it a different color. So now when I plot this, I can see that the true edges range from 20 to up to 80, and they're almost well distributed. But my predicted edges almost range from around 10 up to 40 or 50. So there's, if my predictions were really good, I would see most of the values around the diagonal line. So this means either that the two features that we have selected are not really enough to make the predictions, or that we haven't trained it enough. So here our predictions looks like most of them always range from almost 25 to 40 because they are clustered around this region. But for some of the edges, it's making good predictions. But this is probably because most of the edges actually range between, or are actually less than 40, 45. So to optimize, the model has learned to predict most of the edges from to be between 25 and 40. So if you have a really good data set and the data is actually very predictive, then you will see that most of the dots will be around the diagonal line. Now, once we have trained a model, we can also extract the weights from this model to build our own equation to make predictions. So our first weight, W naught, that multiplies blood pressure, will be W naught equals model dot layers, my first layer, and get weights. And my second weight, W1, that multiplies the second input feature, will be model dot layers weights 1. And my bias will be my weight 1. Then I can print the weight, all the weights and biases. And to actually make predictions without using the model, I can simply do my predictions equal my first input feature, data set all rows and the 0th column, multiplied by weight 0, plus my second feature, data set all rows, second column, multiplied by weight 1 times the bias, plus the bias. And if I print my first few values, these are same as the ones predicted by the model.